Cast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thanks for joining us for another episode of our AMS webinar series. And I want to take a moment to thank all of our AMS subscribers and especially our attendees for making these webinars possible. In this webinar, we're going to be covering a number of special topics in 2.5 axis machining, and we'll get over those topics in just a moment. Some housekeeping tips. If you're just joining us, you can enter questions in the chat window, and I want to take a moment here. If for any reason you can't hear me or if you can't see the screen, please send us a chat in the chat window, and we'll see if we can debug it for you in the background. Also, the last 10 minutes of the webinar are always reserved for question and answers. So we highly recommend that you ask questions and make it as interactive as possible. Not only do you get answers to your questions, but also all the other attendees actually can learn from those questions. And then also we are recording this webinar, and we always make them available to you via a download after we process them, and we'll send you an email about that. Okay, and this, as I mentioned in this webinar, we're covering special topics in 2.5 axis. Now, not all users will be utilizing these topics, but if you do, then you're going to want to refer back to this webinar because it'll give you some really good information. We're going to cover two types of aggregate machining. First, we're going to cover aggregate head machining, where you can actually attach an aggregate head to your spindle, and you can machine in various orientations. Also, we're going to cover disc machining, which is a form of aggregate head machining where you can actually attach a saw blade or other cutting disc to your spindle. We're going to be covering that. And then also we're going to be covering the use of drill banks, or otherwise known as multi-drill heads, where you can drill sets of hole patterns very quickly. This is used mainly in a production setting. So we're going to be going over that. And we're going to be going over knife cutting. This is actually an operation that's been in our suite for a couple of years. But we're going to be going over that, two different types of knife cutting, a swivel knife and a drag knife cutting. And then we're going to wrap it up with how to use machine control operations in your posted G-code files. Okay, so let's get started. First up is the aggregate head machining. In the image, the illustration you see here is just a short segment of a long channel. Now, typically, the aggregate heads are used for cutting right angle cuts on a milling table. If you can imagine a millwork door sitting on your table and you're wanting to cut, say, the hinge pockets or the lock pockets, you can put the aggregate head on, and you can come in and attack that from the side and mill those out very easily. So it utilizes indexed setups. It's just a standard index machining, and Joe is going to go over that. Also, I forgot to mention, my name is Don LaCourse. I'm a senior application engineer for MecSoft, and I'm joined today with Joe Anand. Joe is MecSoft's product manager, and Joe is actually going to be doing the demo portion, and I'm doing the presentation portion. Okay, so aggregate head machining supports all 2.5 axis, 3 axis, and index 4 axis machining operations. So basically, you're doing an index setup to machine 2, 3, or 4 axis operations in that locked orientation. And it also supports all tool types. So it's very versatile. If you've got an aggregate head, you can pay attention and look at this demonstration here that's coming up. Okay, next topic. Disc machining. Now, as you see in the part, we have a rotary disc. It could be a saw blade. whatever type of disc you want to use, you can define it as a face mill, and it is set up as an index, utilizes index setup similar to the aggregate head. And specifically, you can use 2.5 axis slot operations or 2.5 axis profiling operations to cut these using the aggregate saw blade. And as I mentioned, the saw blade is defined as a face mill cutter, with just the large diameter, and the width of the cutter is the flute length of the face mill. Next slide. Now, this is going to be a really interesting topic. If you're cutting a lot of holes in a production setting and a lot of hole patterns, you can get a drill block, which also referred to as a multi-drill head, set to this pattern that you need to machine. And we're going to show you how to set that part up and use the multi-drill block to machine the part that you see here. And as I mentioned, you can use it for machining multiple hole patterns to save you time on the CNC machine. And it supports all of the current drill operation types. This is going to be an interesting one. Next slide, Joe. Okay, we're going to talk also about knife cutting. In this, we have two example part files. One is the one you see here. We're going to be covering drag knife application and a rotary knife. A drag knife is where the knife blade follows the spindle, so to speak. So it has a bearing in the knife tool, and it rotates, and as the spindle moves, it just drags behind it. And then also a rotary knife, where it's a fixed positional knife, and then the rotating is done in the spindle. You can machine sharp corners with a swivel control, where it actually retracts and enters the material in just a small swivel height to allow that drag knife to swivel around and drag behind the spindle. Also, it supports all of the standard sorting controls that we have in our 2-axis operations, distance sorting, directional sorting, etc. Joe? Okay, for our last special topic, we're going to talk about machine control cycles. Now, this is probably maybe a little bit more used than the other topics we're covering. You may have used it already. Anytime that you need to insert some special code into your post-to-G code file that isn't supported directly by your standard operations being posted, you can use what's called a machine control cycle. And you can use one of 4 different machine control cycles, and you can define those for whatever type of code that you want to insert into your posted code. And as you can see in the setup, you can define that machine control cycle where you want it to appear in the setup sequence of operations. So Joe's going to be going over that as well. Okay, so we went through the special topics, just an overview, and Joe's going to be taking a deeper look into each one of these topics, and I think you'll find it very enlightening. Joe?
Thank you, Don. Welcome, everybody. Let's get started without any further ado. So I'm going to start with the aggregate head example first. Quick note, most of the topics that we're going to be discussing here uses our Pro configuration, or at least the 3+2 configurations, where you will need the additional setups. Standard, if you're using the standard configuration, you will have to upgrade to add the multiple setup configuration, because these are advanced topics, and so these require these advanced functionality. as you can see, this part, it's actually a fabricated part. It's a metal part. Customer actually sent it, and we modified it slightly so to remove all IP information from it. And as you can see, this is a fabricated metal part. It's probably pretty heavy. It's sitting on the table, and so to machine this, you really don't want to be rotating the table. So you want to actually typically use an aggregate head, and if you're lucky enough to have a 5-axis machine, you can obviously use the 5-axis machine as well. But so what we're going to be showing here, what I'm going to be showing here is the 3-axis. Let's say you had a 3-axis machine, pretty dumb machine. I'm using the word not as a prerogative, but pejorative, but more as a functionality that is it cannot do rotations. It can only do 3-axis motions. In that case, you can still use our system and use the power of our programming system to create machining toolpaths using aggregate heads, and I'll show you how to do that. First of all, let me go you through the toolpaths quickly, and then I'll actually show you how to program these in this part. So what we have here, the first thing we do is we have to define it as a machine tool, a 5-axis machine tool. The first thing that you want to do in case of an aggregate head. If you're using an aggregate head on a 3-axis, in the CAM system, you still have to define the machine as a 5-axis. And we would recommend using the 5-axis head-head configuration. So this way we are actually rotating the head and not the table, because most parts, typically either in a router application where you have a large door or some part like that, you really don't want to rotate the table. You want to rotate the head. And in this case, it's an aggregate head, and you are rotating the table in fact. And so we set it up as a head. And the reason we do a 5-axis is you can rotate the aggregate head in different orientations. Maybe in some actually in this application, you really don't need a 5-axis. You can do a 4-axis rotation because we're only machining 3 sides here, so you can get away with 4-axis. But just to be general, we've defined it as a 5-axis head-to-head. Head-head configuration. And then I'll talk about the post processor in a bit. This is a special post processor we wrote for the aggregate head, and I'll talk about that in a minute. And then the way we machine this is we're creating a standard setup. I'll turn on the coordinate systems, and these are the coordinate system, the standard coordinate system. The z-axis is the blue arrow that's pointing up, and then the toolpath, we're actually cutting that out, so it basically will fall off that piece. It's a profile operation. And then the next thing we do is we rotate. As you can see, this is the z-axis is now normal to this face, and then we are machining that circular hole there. Again, a profiling operation. And then finally, we're doing a rotation back by minus 90, where you can see the z-axis is pointing this way, and then we're machining that slot. And then once we created the toolpaths, we use this post processor, or we could write something specific for your machine, not necessarily this post. So if I go and do a post all, I'll show you the posted code in a minute. So as you can see here, you see the angle, the standard setup, the angle we've set up as a B angle to come out as 0. So the reason it's coming out as a comment is we're assuming you have a 3-axis machine that's not capable of rotating. So at this point, we put an op stop there with the M00. Actually, you pause to rotate the aggregate head manually. Once you do that, and then you can machine the top, and then the top slot is machined, and then do a rotation 90. That's where we're again pausing to rotate the aggregate head by 90 degrees. So since it's manual, you got to be careful about the kind of rotations you're doing, which direction you're rotating. And then finally, the third operation, we're rotating 270 or minus 90, depending on the type of machine that you have. So those are equivalent. So let me quickly go through how we program it, just as an illustration. I'll go ahead and delete all these operations. For those of you who don't know how to set up the machine, we're basically doing a manual definition, 5-axis head, and then we're doing a standard x-axis as the fifth axis. The primary axis is about the z-axis, which is pretty typical. And then let's say we create a stock. Oh, it's actually we created a stock from selection. So basically, this is a pro feature where we selected this solid model, and that's our stock model. And then let's do a standard setup. So we create a standard setup, normal setup. We'll say generate, and that would be, if you look at the orientation of the z-axis, the blue arrow is pointing up, and so we can machine that part. So I'm going to rename that. We'll call it the standard setup. So as I'm doing this, if you have any questions, yeah, go ahead and type it in the chat window, and Don can either stop me or he can answer by typing in the answers in the questions window. So let's keep it as interactive as possible. Okay, so now I want to machine this. I just want to do a profile operation. So all I'm going to do is go up to 2-axis and do a 2-axis profiling. Select my edge curves. I can do that. So that's what I'm going to be machining. I'm going to use a flat end mill, 1/2 inch. These are the tools that I've already defined, my tool library. I'm going to leave my feeds and speeds standard, loaded from a knowledge base. Clearance plane, as you can see, it's oriented correctly, the clearance plane. I'm going to leave it as automatic. And then cut level is just this important one. If I just do one cut level, if I don't do anything, it's just going to give me one cut. So in order for me to go down and cut this, I need to do multiple cuts. So I'm going to go back to my cut levels, and I can use this total cut depth. I can actually specify by selecting that, and it's 0.375, and I can split this up into maybe 0.15 cuts, and that's the kind of cuts I'm getting. Okay, that looks good. So I can simulate it at this point. I'll turn off the part model. It's fighting for display. So, okay. So I probably don't want to come in that way. I can probably come in, as you can see, I don't want to plunge into metal like that. So that's the nice thing about our simulation engine. So you can go to entry, exit. I can do a long path, do a ramp, and do the same thing. Actually, on the exit, I'm okay. So I'm actually not plunging into material. So there I'm ramping in. Okay, and at the end I'm coming out, and I don't really care about that because I can cut. Okay, so now let's try. Now this is the crux of the whole thing, is how do we machine this side? So for order for us to do that, we create another setup. So we go in there and create a setup, and the way we want to orient the blue z-axis to be normal to this face. So many ways of doing this, but the simplest way in this case is I'm just going to rotate about the y-axis by 90 degrees. If I do that, you'll see the blue arrow is now pointing that direction. So I'm going to generate, and so I'm going to rename that setup. Rotated by 90, I'm going to call it that. And in fact, instead of going back and I can just copy paste this operation, Control C, I'm doing a Control C, and then I'm moving it down here and pasting it. And then all I need to do, and I know the thickness is pretty much the same everywhere, so I don't need to change any of the parameters of the feeds and speeds. So all I need to do is change the control geometry in this case. So I'm going to go remove all, and then select curves and edges. I'm going to select that and other curves. I'm going to generate. So there you go. So it's the same parameters, same cutting parameters, and I can simulate that. So I got these two sides machined. Okay, now let's go ahead and machine the other side. So now if you notice, the z-axis is pointing this way, so we want to orient it, maybe rotate that by y-axis by 180 degrees. So let me create another setup. And I'm going to rotate that twice by, so I'm rotating it this way. Now I'm going to do the same thing. I'm going to rename that, rotate it by 270. Rename. 270 or minus 90, either one is the same. And I'm going to do the same thing. I'm going to copy this operation and then go in here and paste it. And then change the control geometry again. So remove all. Just going to go select. Okay, so it could not find the valid data because the cutter could not get in. The slot is too small. So let's try a 1/8 inch. There you go. So now I can cut that, either that or I can do a slot machining, depending on what you want to do. And I can simulate that. Okay, so let me go back and select my operation. This is, I'm going to go stock from selection. This is a,
Joe, I believe
yeah.
there might be a layer in that file that has the
stock.
yeah, that has a stock defined.
Okay, let's go back and maybe that one. Could be that, I think.
Yeah.
Okay. Okay, stock from selection. Oh, I gotta select the stock model first. Yeah, poly surface, then a stock from selection. Okay, now I can hide that stock model. I think that was this one.
I believe it was layer 1, I think.
Layer 1. Okay, all right. Thank you. Okay, so that's stock from selection. So basically what we did was we selected a poly surface. It has to be a solid model, and that's what starting stock is. And obviously this does not have any of the features machined yet. So we're going to do and then we're going to do the simulation of the next one. Okay, and then finally, okay, so that's pretty much it. That's how you do an indexed machining operation or multiple machining operations. And the key to this is when we output this, let's do a post all. I think we did that already. So the rotations are set up as mentioned previously. So the angle's coming out here, and then the B90. And then finally, we got the 270. We're getting the angle 270. These are coming out as comments. So we're assuming that you're going to be doing a manual rotation of the head, which direction you're going to be rotating. And we do the transformations internally. So the tool positions are coming out in world coordinate system, which means your 3-axis machine can handle it and machine it correctly based on our transformations that we output in the post processor. One of the key things you will have to specify, though, is the gauge length. If your machine tool does not handle rotated coordinate systems like a TCP, then you will have to specify the gauge length. And in the machine, there's this gauge length we'll have to specify, which is basically there's the distance between the pivot and pivot point and the collet end. And this is important because we need to actually, you can read about this in our help file and how we use this to make the transformations so that the toolpath coordinates will come out when you're doing a rotated coordinate system programming, but machining it on a simple 3-axis machine. So that's an important concept that you need to understand.
Joe, we had a question. Um, uh, how to zero out the rotated head? How to zero the machine out with an aggregate head?
Yeah, typically people would zero it out at the table. You can do it at the table or at the top of that.
In other words,
top of the
with
stock.
the aggregate head installed, they're zeroing it out. In other words, they're setting the angle of the head, and then they're zeroing out.
Yeah, so what you'd have to do is have the aggregate head without any rotations. So it's pointing down, the tool is pointing down, and then you're going to zero it out that way.
Okay, okay.
And then once you zero it that way, and then you specify the gauge length in the machine tool, then we will do the transformations using that gauge length.
And there was another question asking about how to program the sharp corners in the pockets. That's one thing you can't do necessarily in CNC, is to actually create a sharp corner with an end mill. So I'm just asking you, Joe, the best way to handle that would just be what, with a smaller end mill, just for the corner?
Yeah, obviously, because of the radius of the end mill, if you're just going to machine it, you're going to leave that corner. So the best way, I mean, in metal machining, if you want really sharp corners, people use electrodes. They machine the electrodes, the male portion of the electrode, and actually sink the electrode in.
Yeah, burn it right out.
Right. If it's wood, obviously you're not going to be using that method. So there's you'll have to use a smaller tool and come in maybe with a remachining operation with small tools and come in and clean it out as much as possible. That's pretty much it. I mean, we really can't get to those sharp corners in CNC because of the radius. The physics of the physics of reality doesn't help us there. So
well, that's what EDM machining is for.
Right. Yeah. Okay. So we need to be stepping it up a little bit. So let me go on to the next, which is the saw machining. The reason we club this together is because we can use saw machining using an aggregate head. If you don't have an aggregate head, as Don mentioned, you can define the saw as a disc tool, and similar to what, let me show you though, like a face mill. So which is what we've defined here as a face mill, and you can see the flute length defines the thickness of your saw or disc tool, whatever. Here we've defined that as a 3 millimeter. This is a millimeter file, so 3 millimeters. If you don't have an aggregate head, the only thing you can do with this is kind of like, face the top of it, maybe come in and cut it. But let's say you have some slots like that that you want to machine, you want to actually do some rip cuts on it. And the way you would do it, there's multiple ways you can do it. You would obviously have to resort to index machining and have an aggregate head that actually rotates your saw in the right direction. So I'll show you what we have done here. The two ways of machining this. So this is we've actually had a rotated. So this is our standard setup where the z-axis is pointing up, and then we did a rotation over here. So the z-axis is pointing this way, and then I've used a 2.5 axis profiling operation. So basically, I've selected to machine that slot. I selected that edge curve down there. And then I created a 2.5 axis machining operation. So if I simulate that, I go in and simulate play. So coming in that way, notice the retract and the engage directions. They're along that blue axis, which is basically the Z axis of the rotated head. So that's how you do rip cuts like this. And then you can also, there's another method, you can use T-slotting as another operation. In this case, I've selected this edge and I've used the T-slotting operation. T-slotting is a little more complicated. I'm just showing it to you. So there's an option. Some people can think of it. I mean, it's more logical to think of that slot as a T-slot. in this direction. So some people might like to think of it as a T-slot operation and machine it as a T-slot operation. So that's what we've done here. I've selected this curve as the top edge of the T-slot, and then I've selected and I've specified this distance, this depth. The start depth is actually starting from here to here. That's about 219.5 millimeters. So that gave me this tool path. So I can simulate that. It basically cuts the same thing. And then to machine these slots that are going in the other direction, obviously you need to create a new setup. So you need to rotate the saw in that direction, so it's normal to that, so which is what we have done here. So the Z-axis is pointing in that direction. And then I've selected these two curves, which define the slot, and use the two-axis profiling. I'm coming in that direction and machining that. Okay, and you might be asking, how did I do that? How did I selected the curve, but how is the cutter actually going in? There's a little trick in there that I've employed, which is negative stock. Some of you might be familiar with that. What I've done here is the depth of my cut is I've used that as 3 millimeters. So I said, give me a 3 millimeter cut, which by specifying a negative stock. So basically it's cutting into the material by that much. There's one caveat with the negative stock. The negative stock can be higher than the tool radius. So as long as your cut depth is not deeper than your tool radius, in this case it doesn't make sense because your flute is going to interfere anyway. So it works out pretty well. So I gave it a -3, and that's how I got that. But if you're using T-slot, you don't need to specify anything like that because you're not doing, you're actually machining, you're telling the system you're actually machining a T-slot. So you just define give it the parameters of the T-slot and do a finishing operation. So, okay, so I hope that is clear. Any questions on that, Don? Okay, let's moving on to our next topic. We're going to be talking about drill head programming, drill block programming, or also known as multi-drill head programming. What I'm going to be showing is an example of a 4 drill bit drill head, multi-drill head that I have. I'm going to show you the picture of what I have. And this is basically the picture of a depiction of what I have in terms of the multi-head drill block. So it's got 4 tools, tool number 1, and this is tool number 2, tool number 3, and tool number 4. And this drill head, we can independently turn on or off any of these 4 drills. We can keep them all turned on, or depending on the cut pattern or the hole pattern that we have, I can turn on just a few. And we'll be talking about how we're going to be programming those the patterns that I showed you. Okay, so let's before we go on, I want to talk about the part file a little bit. Let me move. What I have on my screen is a Rhino file. This is a typical file that you might be machining with. This got a lot of hole patterns. This has got 4 hole patterns on the corners, and then there's 1 hole pattern in the middle. The hole pattern are all equally spaced holes. They're spaced by 0.25 inches. And as you can see, there are quite a few different configurations as far as the hole patterns are concerned. But they're all of the same size holes, same depth, and so I can conceivably use my multi-drill head to program these. Okay, let's talk a little bit about the concept of programming a multi-drill head. So in what you're really programming is a tool, just like you would program a single drill tool, but there is one preferred anchor position or tool, a number that you're programming, the tool position that you're programming. So looking back at the station here. So typically you would be programming this tool number 1 that's shown here, which is in the lower left corner of the drill block. And so that's the position you're going to be actually programming in terms of the actual drilling operation. But you will be turning on and off any one of the other tools, or even the tool one. You can either turn that on or off. So how do we go about turning these off and on, and how do we control this in our CAM system? Before we get into that, I want to talk about a few concepts that we need to be clear on. One of the things is assignment of binary codes for each of these tools. So I have a table here that basically assigns a binary code for each of the tools. The table, the tool number on the left, I have 8 tools listed. Potentially you could have a multi drill head or a drill block that has 8 tools. In my case, I have 4 tools, but just for illustration, I've shown you 8 tools here, and the corresponding binary code for each of these tools. So for tool number 1, the binary code is 1. Tool number 2 is 2. Tool number 3, it's 4. Tool number 4 is 8, and so on. For those of you who are not familiar with binary codes are basically start with number 1, and the next code, the next binary number would be multiplied by 2. So 1 multiplied by 2 gives you 2. 2 times 2 gives you 4. 4 times 2 gives 8. So that's how the binary numbers are ordered. That's the assignment. So for each of these tools, you're going to assign a binary code. And then just to turn on or off any of the tools, just to turn on the tools, not off, just to turn on the tools, you're going to add the binary codes associated with the tools that you want to turn on. So let's say you wanted to turn on tool numbers 1, 3, and 4. So what you're going to do is you're going to add up the binary codes of those 3 tools, which in this case would be 1, 4, and 8. And that gives us binary code 13, or a total of 13. And then we would create a single tool with that number 13 as the tool number. And that's the encoding step that we're doing next. So once we have that, we can program using that tool in this anchor position, or the tool number 1 position. And then when we output it, post-process it, the post processor will take the number that you have encoded in that particular tool and do the necessary decoding and output the corresponding G code for your controller. So let's go through that very quickly in this part file. Okay, so what I have here, let's talk about this pattern, whole pattern on the lower left corner. So here, if I employ my 4 drill head or 4 drill block, I need to turn off drill number 4 in this particular case, because I'm not there's nothing to drill on that location. So I would need to turn on 1, 2, and 3. The drills 1, 2, and 3 in my drill block. So what I need to do is I need to go back to my binary table and add the binary numbers associated with these tools, which would be 1, 2, and 4. So that gives me 7. And then I create a tool, it's tool number 7, which I've already done. Here I'm calling the LLC, half-inch LLC, which is lower left corner. And I've given it a tool number 7. I've programmed a tool, created a tool with tool number 7. And then I'm going to use that tool when I program this whole pattern, so which I've already done. I've taken my anchor hole and using that as the drill bit, a drill hole for the drill operation. I've created a drilling operation here using the lower left corner drill bit. So I really don't care about the depth at this point. This is just for illustration purposes. And now, even though I'm just programming the anchor bit, and since I'm using the drill tool, which has got the binary code encoded, when I create this tool path and output it using the correct tool path post processor, it'll be decoded correctly. So let me show you that. Just select this, and I have a post processor selected already. This is an example of our latest programmable post. For those of you who are not familiar with programmable posts, I'll talk about that in a minute. But this is very exciting development in our system since 2021, release 2021. which you can do quite a bit of logic using Python programming language. I'll show in a minute, but let's see how that post operates. So when I select this operation and I do a post process, you'll see that this particular tool, which I had tool number 7 encoded in it, is coming out as 1, 2, and 3. So we're turning on tools 1, 2, and 3 in my drill block when this gets output. So which is exactly what the pattern we want. The machine, that pattern, we need tools 1, 2, and 3 output. So let's talk about the lower right corner. In this particular case, we have to turn on tools 1, 2, and 4. And 4 is the binary code 8. So 8 plus 2 is 10. 10 plus 1 is, gives us 11. So now I've already got a tool. Lower right corner, I'm calling it the LRC, and it's got 11. I got a tool number 11 encoded. And then I'm selecting this drill hole, and I've already created a drill operation with that tool selected. So when I post process this, you'll see the correct tools being turned on. So you'll see tools 1, 2, and 4 being turned on at the output level. So this is how you would program hole patterns. A couple of caveats. One is a hole pattern like this on the top right corner. Let's call it the upper right corner. What we have here is we have 3 holes, but the anchor hole is not being drilled. So the lower left corner is not being drilled. So even though it's not being drilled, we actually, in our CAM system, we have to create an operation that actually creates a drill operation there, or a drill toolpath that goes right there. So that's why I've created this circle to represent the location of the anchor bit, and I've created my drill operation to drill that hole. And then I'm using the URC drill bit that I've already created. So with the binary code for that would be the binary addition of 2, 3, and 4. And I believe that's 13, if I'm not mistaken. But that's 14. Okay, tool number 14. So if I post this, you'll see 2, 3, and 4 being turned on. So that's even though 2, 3, only 2, 3, and 4 are turned on, even though we have programmed this anchor hole, this is not going to be machined. Only these 3 holes are going to be machined on your machine tool. Finally, one caveat about the patterns. We had repeating patterns, and if you have a pattern like this, the idea is you can look for repeating patterns. In this particular case, I noticed that the upper right 3 holes are very similar to these lower left corner pattern. So which means I can use the same tool, and same tool that I used for this lower left corner. So let's talk about that one. So I'm programming that hole, and I'm using the same tool that I use for the lower left corner. As you can see, it's selecting the lower left corner. So when I post process that, you should see 1, 2, and 3 turned on. So 1, 2, and 3 turned on. I guess the idea here is to look for repeating patterns and use the same tools for those repeating patterns. So that's something that you as a programmer need to be cognizant of. So let me go ahead and post the entire setup, and let's see how these numbers turn on. Okay, here we go. So the first operation, we got T1, 2, and 3 turned on. Second one, which is this pattern, is 1, 2, and 4. 1, 3, and 4, I believe, is for this. 2, 3, and 4 is for that one. And then 1, 2, and 3, which is similar. This is the same similar patterns, the lower left corner. And then you have the 2, 2, and 3, which is just these 2 holes, 2 and 3 being machined. And finally, T0 in this particular controller at T0, when you employ a T0 code, it'll basically retract all the drill bits, and you're not machining anything at that point. So that's all drill bits are up at that point, and you typically do it at the end or at the beginning before you actually engage any of the tools. So that's pretty much it in terms of programming. And I also said I would want to talk very briefly about our programming language that we use. So as I said, we have two types of posts. One using our legacy posts, which are macro posts, and most of you are familiar with that. In 2021, we released something called the programmable post, which uses a Python programming language. And you can actually, let me show you how one of those Python programming language posts looks like. Let me go to the. So this is, I'll open it up in Notepad++. And this is an example of the Python program that references the SPM file or the legacy file. It's getting most of that information from the SPM file. And then if you wanted to override certain behaviors in the SPM file, you can write specific blocks of code to actually override. So in this particular case, we've written a decoder that'll take the tool number that we have assigned and decode it to turn on the correct tools in the drill block, the multi-drill head. So this is an example, and it can be very complex. We can do all kinds of things using the programming language, and so we're pretty excited about that. If you have any questions about that program, the programming language itself, we can help you with that.
Joe,
Yeah.
do you need to have the programmable post to do the drill block? It won't work with the legacy post?
There could be controllers that we can handle with the legacy posts, but typically, if there's some complicated decoding that's necessary, we would require the programmable post.
Okay, so we would evaluate this with the user on a case-by-case basis.
Right. Exactly, depending on the controller. And then, yeah, and we would, these programmable posts, for us to write those are extra cost items. And we do have our programmers who are experienced in Python programming language actually write this. And so we're pretty confident that we'll be able to handle a lot of those controllers out there on the field.
Another question: do you zero the machine out with the drill block head attached with tool number one? Is that how you do it, or?
Yes, that's typically how it would be done.
Okay.
Yeah, so you can think of the tool number one or the anchor tool, depending on whatever tool that is, as the tool you're programming. And then all you're doing is turning on the other tools. So there's no independent zeros for the other tools. It's only for the anchor tool.
Okay.
Okay, so moving on, let's talk about the knife machining. These are some of the more, we talked about some of the more complicated, more interesting ones, but the knife machining operation is actually part of the standard configurations. And for those of you who don't know, there are two types of knife machining that we can do. I'm going to show you some simple examples here. So let's say you have an application where you're just cutting out a shape like this out of a sheet of material, which is where drag knives typically will be used, probably for leather or something soft material like that. The idea of drag knife, as Don mentioned, is when there's actually a bearing in the knife itself, and so you don't need to actually rotate the knife. It's kind of like a rudder on a boat. As the boat starts to go in one direction, the rudder actually orients itself in the direction the boat is traveling. So very similar to that, the drag knife, in the direction that the knife is traveling, the spindle is traveling, the knife will orient itself. And the way it's done is by specifying this swivel depth. So if you look at this picture here, the swivel depth is important where when the knife comes into contact with the material, it actually does a swivel operation, and it moves in the same direction as the cutting direction. So the swivel depth is important to specify. That it's actually got to be slightly inside the material. And so that's what we've done here. And you can see the toolpath. I can simulate that. So the idea here is we have selected this knife as a swivel type knife. And then very similar to a profiling or engraving operation, we selected the curves. But you can look at the corners. You can see the knife goes up to here, picks up, and does a rotary transfer motion, and then comes back down in here, does the orientation of the axis of the spindle, and then goes cutting in that direction. Let me run the simulation. Oops, sorry about that. Let me rerun it. So there's the knife, does a swivel. The simulation probably is not very accurate in terms of how the swivel happens. On your machine, it's probably the swivel will happen before or after that engages into the material. But as you can see, the swiveling is happening before in our case, but that's just an artifact of our simulation engine. So there you go. And a quick mention about the knife itself, that you can define a knife tool in our system. So the parameters are, you can do a knife can have a height on the right side that is different from the left side. And then it can also have an offset from the center where it's actually cutting. The center line of the knife is actually offset from the center of the spindle. So that's so it's quite general in that sense to be able to define your knife. Okay, then I'm going to show you an example of a rotary knife. A rotary knife is where the knife is actually rotated in place or rotated into a certain orientation and locked into that orientation. And here's an example. This is actually a customer from France did this. They're actually cutting speaker, I think speaker fabric around speakers or something like that. So in this particular case, the outline we machined using a rotary knife, and then in the grid pattern or the grill pattern in there also was machined using knives, using the same knife. So let me go back into the operation and I'll do the simulation here. So this was defined as a rotary knife. And also the important thing here to observe is the corner angle limit, which we have specified as 10. So whenever you hit a corner that is greater than 10 degrees or less than 10 degrees, it's going to actually pick up the cutter or the knife in this case and do a rotation and then come down in the correct orientation, come back down and then machine that part. That's what you're seeing here in the corners. It's coming in here and saying, okay, that corner angle is greater than 10 degrees, so I'm going to pick up and then do the rotation. So let me run the simulation. So it's picking up. And the rotations are created as rotary axis rotation. So the cutter or the post process needs to be set up so to correctly handle it. So let me post it. Okay, as you can see here, you can see the angles that are being output: 331, 333, 334. So as it's coming around the circular pattern, you can see the swivel is happening here. So your post process needs to be set up and to be able to handle the rotations, and we can help you do that. Okay, any questions there, Don?
There was one question about other types of cutters like circular pizza type cutters, how they would be defined. Currently, I don't believe you can define any other than just a straight blade knife. Is that correct?
That's correct. Yes.
Okay.
Yeah.
Okay.
You can possibly use a disc, like a shell mill, and define it, but
yeah,
that's what they're asking. Yeah.
Yeah, that would work.
Oh, Yeah, one other quick note on this one, this pattern here, we have a set of curves. Currently in our 2021 version, we assume that the knife is bidirectional, so the cutter can come and cut this direction, pick up and go and cut the other direction without a problem. But in some cases, some of you might have unidirectional knives. In that case, what you'll have to do is you'll actually have to sort the curves correctly so they're pointing in the right direction for the rotation to take place. This has been fixed in the 2022 release, but those of you running 2021 now and the knife operation is just a quick note for you to make sure you orient the cuts correctly or the regions correctly. Okay, so last but not least, we're going to show you the machine control operations, the use of machine control operations. This is the part that I believe Don put together. The idea behind this is more to show concept than anything else. What he's defined is he's created sorted these operations by tool type. And we're assuming in this particular example anyway, that you have a machine that has a manual tool changer. You don't have an automatic tool changer, so whenever the tool needs to be changed, you have to do an op stop and get up there to some location and then do a manual tool change. So that's the reason we have sorted this by tools. And then to introduce the actual manual tool change, we have introduced a operation or a machine control operation. And then again, then the tool is changed, and then we got the 1/2-inch deep drill to do the drilling operation. And then once the drilling operations are done, we create another op stop operation and then go into the final tool, which is a flat end mill of a 1/2-inch to do all the other operations. The way you define a machine control operation is you go up here to utilities. Here, this is a machine control operation where you specify, and there are 4 machine control cycles that you can define. This is a system limit of 4. So, and basically each of these cycles can be defined to output whatever code that you want to come out on the machine. So we're showing this example here. So I already created the machine tool, so operation, so I'm going to remove it. And I'll show you the posted file. Okay, if you look at it, so here I'm going to search for the opcode. Okay, as we hit the machine control operation, which is this op stop, the first op stop operation, we have defined the post to actually put a M00, which basically stops the operations. And then a controller message comes up saying load tool drill 1/2-inch at this point. So then the user actually will have to load it manually. Then once the loading is done, then the coolant is turned on, and then it's continues on to the next operation, and until it hits the next one. And the same thing happens here. Now we load the flat end mill, 1/2-inch flat end mill, to proceed with the previous the subsequent operations. So this is just an example of how you can set up the op stop or any machine control operation. And the only thing you need to do here in this case is define the code in the post processor for each of these cycles. So if you go pick up cycles in the post processor generator, you see these 4 machine control cycles that I mentioned. So in this particular cycle, code number 1, this is what we're outputting. We're outputting a comment. You're saying specifying operation to stop, you allow manual tool change, and then an M00. And that's what you saw that was being output in the G code. This is pretty useful if you have any kind of situation that is specific to your environment. For instance, some machine tools have zones of machining. And then if you wanted to specify a certain zone for machining, you can create a machine tool, machine control operation and specify the code, and that'll define that particular zone. That's another example of how you can use these machine control operations.